put yourself in the middle, and I tell you this universe was born 13.7 billion years ago. So let's go out to the circle, to the sphere around us, go to the spot that's 13.7 billion light years away.
At first, there is nothing. No stars, no galaxies, no light at all, just darkness. It looks like empty space. But this isn't where the universe ends. This is where our view ends. Beyond this darkness, the universe continues. But the light from those places has not had enough time to reach us yet. As we move closer, something begins to appear. A faint glow, then structure, and then everything. Every point of light emerging here is not a star. It's a galaxy, an island of billions of stars drifting through an ocean of galaxies that stretches across the cosmos. And this is only what we can see, because the region of space we can observe is only a tiny portion of the universe that actually exists. Over the next few minutes, we're going to travel across that visible cosmos. From our own planet, past distant worlds and alien solar systems, through galaxies containing trillions of stars, into enormous clusters of galaxies, across superclusters hundreds of millions of light-years wide, and finally into the vast cosmic web that connects the entire observable universe. Along the way, you'll see structures so large they challenge our understanding of scale. You'll discover why space only appears empty, why the universe formed this strange cosmic network, and why everything we can observe may be only a small region of something far larger. Because when we finally reach the edge of the observable universe, the questions become even stranger. Is our universe only one of many? Could there be other universes with completely different laws of physics? And what lies beyond the cosmic horizon we can never see? But before we cross billions of light years of space, we have to start somewhere familiar. A small rocky world orbiting an ordinary star in a quiet corner of one galaxy. Earth. From here, the universe feels familiar. Distances make sense, space feels empty, and everything important seems close. That's because this is the only place our intuition was ever built for. Earth is where our ideas of far and near come from, where scale still feels manageable. But those ideas don't survive once we start to leave. And as we move outward, step by step, you'll see exactly where they begin to break. The first place it happens isn't at the edge of the universe. It's much closer. Far enough that Earth stops feeling like the reference point. Far enough that planet starts to mean something else. That place is Jupiter. At first glance, it looks like just a larger planet. But Jupiter isn't simply big, it's different. Jupiter contains more mass than every other planet in the solar system combined. If it were only a few dozen times heavier, it wouldn't be a planet at all. It would be a star. The line between planets and stars is thinner than most people realize. Jupiter sits right on that boundary. Its gravity dominates this entire region of space. It bends the paths of comets, captures asteroids, and quietly reshapes the orbits of worlds far smaller than itself. There's a real chance that Earth exists in its current form because Jupiter is where it is. And yet, for all of its size, Jupiter is still small. More than 1,000 Earths could fit inside it. And compared to the Sun, even Jupiter disappears. Its moons tell the same story. Europa hides an ocean larger than all of Earth's oceans combined. Ganymede is bigger than Mercury. Io is torn apart by gravity, its surface reshaped by constant volcanic eruptions. These aren't moons in any familiar sense. They're worlds. And Jupiter itself isn't a place you could ever stand. It has no solid surface, only layers of gas, crushed deeper and deeper until pressure turns matter into something almost unrecognizable. This isn't a world you land on, it's a world you fall into. And as immense as Jupiter feels, it's only the beginning. Because once scale breaks here, it never fully comes back. Jupiter feels enormous. But the moment we step back and look toward the center of this system, even Jupiter begins to disappear. Because the object that truly dominates this region of space is not a planet. It's the star everything here revolves around, the Sun. From Earth, it feels immeasurable. A blazing sphere that dominates our sky and controls the motion of every planet we know. More than 1 million Earths could fit inside it. And nearly all of the mass in the entire solar system is locked inside this single star. Every second, deep inside its core, about 600 million tons of hydrogen are crushed together and fused into helium. In that reaction, a small fraction of the Sun's mass is turned directly into energy. The light leaving the Sun today actually began its journey in the star's core hundreds of thousands of years ago, slowly working its way outward before finally escaping into space. Right now, our Sun is in the most stable period of a star's life. Astronomers call it the main sequence. It has been here for about 4.6 billion years, quietly burning hydrogen in its core. And it will likely continue doing so for another 5 billion years. Eventually, the Sun will swell into a red giant, growing large enough to consume the inner planets. But that story is far in the future. For now, the Sun is simply an average star in the calm middle of its life. And that's the most surprising thing about it. Because as we move farther away, something unexpected happens. The Sun stops feeling like the center of everything, and slowly, it becomes just another star. Far beyond Neptune, past the last familiar world in our solar system, the Sun's gravity continues to reach outward into an enormous cloud of frozen debris. This region is called the Oort cloud, a vast spherical halo of icy remnants left over from the birth of the planets more than 4.5 billion years ago. Some estimates suggest this distant cloud could contain trillions of comets, and it may stretch nearly a light year from the Sun. That means the edge of our solar system may already lie almost halfway to the nearest star. Out here, the Sun no longer fills the sky. It becomes just another bright point among thousands of others. But the distances between stars are far larger than most people realize. Even traveling at the speed of light, the fastest speed the universe allows, it would still take more than 4 years to reach the closest star system. That star is called Proxima Centauri, a small, dim red dwarf orbiting the Alpha Centauri system. And despite being the closest star to us, it is still more than 40 trillion kilometers away. Which means something extraordinary. Everything we've seen so far, every planet, moon, comet, and asteroid in our solar system, exists inside a tiny bubble of space around a single, ordinary star. And beyond that bubble begins the galaxy. Beyond the boundary of our solar system, the distances between stars stretch across scales that are almost impossible to imagine. If our sun were the size of a grain of sand, the nearest star would be more than 30 kilometers away. And between those two grains of sand, there would be almost nothing. Our sun, once the center of everything we knew, is only one star in a galaxy filled with them. As we continue to move outward, those distant points of light begin to organize into something far larger. A pattern, a structure, a vast disk of stars, gas and dust, spanning more than 100,000 light-years from edge to edge. This is the Milky Way Galaxy, our cosmic home. Inside this single galaxy are an estimated 100 to 400 billion stars. Many of those stars have planets. In fact, astronomers now believe that most stars in our galaxy are surrounded by planetary systems. So far, we've confirmed the existence of thousands of exoplanets, and many of them orbit their stars in regions where liquid water could exist. Worlds with oceans, atmospheres, weather systems, places that, at least from a distance, don't look entirely unlike Earth. With hundreds of billions of stars in the Milky Way alone, even a tiny fraction of habitable worlds would mean millions, perhaps billions, of planets where life might emerge. But life in the universe may not look anything like life on Earth. Here, life is built around carbon chemistry, with water acting as the universal solvent. But carbon and water are not the only possibilities. Some scientists have proposed that life could form using silicon-based chemistry, or in environments where liquid methane or ammonia replace water entirely. On worlds far colder than Earth, entire ecosystems might exist inside hydrocarbon lakes. And in extreme environments, life might even draw energy directly from radiation or chemical reactions within rock. In a galaxy this vast, nature has had billions of years to experiment, which means that somewhere among these countless stars, there may be forms of life built from chemistry we've never seen before. And yet, within this enormous system, our solar system occupies only a very small corner. We orbit the galaxy about 27,000 light-years from its center, drifting through one of its spiral arms. At the speed our sun travels, it takes more than 200 million years to complete a single orbit around the Milky Way. That means, since the dinosaurs went extinct, our solar system hasn't even finished one full trip around the galaxy. But the most extraordinary discovery lies at the heart of the Milky Way. Because at the center of this vast stellar system, there is something even stranger. At the very center of our galaxy, astronomers discovered an invisible object with the mass of about 4 million suns. Yet all of that mass is compressed into a region smaller than the orbit of Mercury. This object is known as Sagittarius A, a supermassive black hole. The boundary surrounding a black hole is called the event horizon. Once anything crosses that boundary, gas, dust, planets, even light, nothing can escape. Not because the black hole pulls objects inward like a cosmic vacuum, but because space-time itself is warped so severely that every possible path leads deeper inside. Near this boundary, gravity becomes so intense that time itself begins to slow down. To a distant observer, a clock falling toward the event horizon would appear to tick slower and slower until it almost stops entirely. Stars near the galactic center race around Sagittarius A at millions of kilometers per hour, tracing enormous orbits that reveal the immense gravity hidden there. And sometimes, when matter drifts too close, the difference in gravity between one side of an object and the other becomes extreme. The object is stretched longer and longer into thin strands of matter, a process scientists call spaghettification. Despite their name, black holes are not completely black. According to quantum theory, they slowly release a faint glow of particles known as Hawking radiation. Over unimaginable periods of time, this radiation may cause black holes to slowly evaporate. A black hole the mass of our Sun would take about 10 to the power of 67 years to disappear, far longer than the universe has existed so far. Black holes also collide. When they do, they send ripples through space-time itself, distortions in the fabric of the universe known as gravitational waves. These waves were first detected on Earth in 2015, confirming a prediction Albert Einstein made a century earlier. And Sagittarius A is not unique. Astronomers now believe that nearly every large galaxy in the universe contains a supermassive black hole at its center. Objects so powerful that they can influence the formation of entire galaxies. When we look beyond the Milky Way, we find galaxies where these objects grow even larger. The nearest major galaxy to our own is Andromeda, a vast spiral galaxy more than 200,000 light-years across, containing around 1 trillion stars. At its center lies a black hole more than 30 million times the mass of the Sun, nearly 10 times larger than the one in our own galaxy. In the galaxy Messier 87, astronomers discovered a black hole containing over 6 billion times the mass of our Sun. This was the black hole whose shadow was photographed in 2019, the first direct image of one of these cosmic giants. And some galaxies contain black holes even more extreme. In distant quasars, astronomers have measured black holes with masses exceeding 40 billion suns. These objects sit at the centers of galaxies that blaze so brightly they can outshine every star within them. As matter spirals inward toward these enormous black holes, it forms a disk of superheated gas that can reach temperatures hotter than the surface of many stars. Powerful magnetic forces can launch jets of particles from the poles of these disks, streams of energy that travel across thousands of light years, sculpting the gas from which new stars are born. In this way, supermassive black holes may act as regulators for entire galaxies. Too much gas falling inward, and the black hole erupts with energy, blowing material outward again. A cosmic balance between collapse and creation, which means the fate of billions of stars may ultimately be influenced by a single object hidden deep within a galaxy's core. And yet, even these enormous structures are only small parts of something much larger. Because the Milky Way, Andromeda, and Messier 87 are only 3 galaxies among trillions. But as astronomers began mapping galaxies across the sky, something unexpected appeared. Galaxies are not scattered randomly through the universe. Gravity gathers them together. Small collections of galaxies, sometimes only a few, sometimes dozens, drift through space as gravitational families. Astronomers call these systems galaxy groups. Within these groups, galaxies are not still. They orbit one another, pull on one another, and sometimes they collide. When galaxies meet, the result is not a violent explosion. Stars are separated by such immense distances that most pass one another without ever touching. Instead, gravity slowly reshapes both galaxies. Their structures stretch and twist, forming vast tidal streams of stars that can span hundreds of thousands of light years. Over time, entire galaxies can merge together, forming larger and more complex systems. What looks like chaos in these encounters is actually the quiet work of gravity, sculpting the universe on enormous scales. And galaxy groups are only the beginning. Because across the cosmos, these small families gather into something far larger still. Galaxy groups are only the beginning. Because these small families of galaxies do not exist in isolation. They themselves gather into far larger systems. These enormous collections are known as galaxy clusters, regions where hundreds or even thousands of galaxies are bound together by gravity. But even galaxy clusters are not scattered randomly through space. When astronomers began mapping the universe on its largest scales, they discovered something extraordinary. Clusters themselves gather into structures so vast they stretch across hundreds of millions of light years. These immense regions are known as superclusters. Our own galaxy belongs to one called Laniakea supercluster, a cosmic basin containing more than 100,000 galaxies, all slowly drifting toward a common gravitational center. Yet even superclusters are not the final layer of structure. When the distribution of galaxies is mapped across billions of light years, an even larger pattern begins to emerge. Galaxies and clusters trace enormous filaments of matter threading across the cosmos. These filaments connect superclusters together in a structure astronomers call the cosmic web. Between these filaments lie vast cosmic voids, regions of space so empty that a galaxy could travel there for hundreds of millions of years without encountering another. On the largest scales we can measure, the universe does not resemble chaos. It resembles a network, a vast cosmic structure woven by gravity itself. This visualization of a computer simulation showcases the cosmic web, the large-scale structure of the universe. Each bright knot is an entire galaxy, while the purple filaments show where material exists between the galaxies. To the human eye, only the galaxies would be visible, and this visualization allows us to see the strands of material connecting the galaxies and forming the cosmic web. This visualization is based on a scientific simulation of the growth of structure in the universe. The matter, dark matter, and dark energy in a region of the universe are followed from very early times of the universe through to the present day, using the equations of gravity, hydrodynamics, and cosmology. The normal matter has been clipped to show only the densest regions, which are the galaxies, and is shown in white. The dark matter is shown in purple. The size of the simulation is a cube with a side length of 134 megaparsecs, 437 million light years. The camera choreography is a straight line path through the simulation. The camera accelerates from a standstill at the start, flies at a constant speed, and then decelerates to a stop at the end. The cruising speed of the camera is 250,000 parsecs per frame, or about 20 million light years per second, at 24 frames per second. That's more than 600 trillion times the speed of light. And strangely, this structure bears an uncanny resemblance to something far more familiar. Seen from the right perspective, the cosmic web looks strikingly similar to the network of neurons inside a living brain. Two systems separated by unimaginable scales, one spanning billions of light years, the other contained within a human skull, yet both shaped by the same fundamental principle: connections. You've seen why space only appears empty, how gravity slowly gathered matter into galaxies, clusters, and superclusters, and how those structures stretch across the universe in vast filaments forming the cosmic web. You've seen how everything we observe is part of a much larger cosmic architecture. And after crossing planets, stars, galaxies, clusters, superclusters, and the immense filaments of the cosmic web, we arrive back at the boundary where our journey began. The edge of the observable universe. A sphere of space about 93 billion light-years across, containing perhaps 2 trillion galaxies, each filled with billions or even trillions of stars. Everything we have explored, from distant planets to the vast architecture of the cosmic web, exists within this enormous horizon. But this boundary is not a wall. It is not the end of the universe. It is simply the farthest distance that light has had time to travel since the universe began expanding about 13.8 billion years ago. Beyond this horizon, space continues, unseen, and possibly without limit, which means something extraordinary. The universe we can observe may be only a small region of something far larger, a tiny bubble of visibility inside a cosmos we cannot fully see. And when scientists try to understand what might exist beyond that horizon, some of the strangest ideas in physics begin to emerge. Some researchers suggest our universe may be only one region within a vast multiverse, a collection of many universes, each with its own laws of physics. Others propose that space itself may contain hidden dimensions beyond the 3 we experience. And some theories even suggest that reality may be far more complex than our current understanding allows. Because when we reach the limits of what we can observe, our questions stop being about distance and begin to touch something deeper: the nature of space, the origin of the cosmos, and the fundamental structure of reality itself. And perhaps the greatest mystery of all is this: out of the unimaginable vastness of the universe, on one small planet, around one ordinary star, in one quiet galaxy, the cosmos produced something remarkable. You. A mind capable of looking out across billions of light years and asking questions like, are we alone in the universe? How many other worlds might be looking back at the same stars we see? Is our universe the only one that exists, or just one small region in a vast multiverse beyond our horizon? And perhaps the most mysterious question of all: why does a universe capable of creating galaxies also create minds capable of understanding them?
Interesting thing about the universe in which we live, as long as there's galaxies that get overtaken by this expanding horizon, you will always bear witness to the birth of the universe, because somebody is always being born. The interesting part is if the signature of the Big Bang goes away, that would tell you that your horizon washed over a region of the universe where there are no more galaxies to show you their birthday clothes. That would tell you that you in fact reached the edge of the universe.